Hi. So I'm going to be talking about how to build a scalable Python gRPC service using Kubernetes. So I only have an hour, and I'm going to be talking about like many different types of concepts. So I'm sure that many of you are kind of new to things like gRPC and Kubernetes, and so instead of giving you a really, really deep dive into each of these, I'm going to be just giving you mostly an introduction to each of these, and then hopefully whet your appetite in terms of actually, going back and researching these later. So, just as an kind of an introduction. My name is Ian Lewis. I work at Google as a developer advocate on the Google Cloud Platform team. I work in the Tokyo office. I come here to Seoul pretty often for travel, to go to events and things like that. The type of work that I do is mostly to interact with developers and to act as kind of the in-between person between Google and outside people who want to use Google Cloud Platform and our APIs and things like that. I'm also on Google Plus or Twitter if you're into that sort of thing. So you can follow me there. And you guys might have seen me before. Like that's actually me there. Behind all of the Korean lettering. So that was a picture taken from PyCon Korea last year. So I'm famous in Korea. So all of you know me because you've seen my picture before, obviously. But I'm also involved in PyCon JP as well in Japan. So I was one of the I was around when PyCon JP was kind of originally formed and created, and around when we did our first conference back in 2011. So we have a kind of nonprofit company or organization that we use to manage the money from the conference and to help sponsor other types of PyCon events, and I sit on the board of that nonprofit organization. So I kind of don't do a lot of work there because I'm pretty busy with work, but I'm at least involved in that. We're also doing a PyCon Japan this year in October. So and I don't think it's like quite sold out yet. So if you really want to go, you can. Still buy tickets at pycon.jp. But the main topic that I want to talk about today is how to build like an actual Python service using gRPC. And so here's the agenda for what I want to talk about today. First I'm going to talk about gRPC concepts. So give like kind of an introduction to what gRPC is and why it's beneficial and why I think that you should use it. And then after that, I'm going to talk about how to use gRPC with Python. gRPC is a kind of cross-platform thing, so it works with a lot of languages. And I'm going to specifically talk about Python in this talk. And then after that, I'm going to talk a little bit about containers and Kubernetes and how you might actually deploy that service, and give a little bit of the concepts around how you would deploy that and in using Kubernetes, and talk a little bit about what Kubernetes is. And then finally, I'm going to be actually talking about how to actually run the service. So then taking the service that we talked about in the first two bullet points, and then actually how to deploy that in Kubernetes. And as I'm going along, I might do some kind of pop in and out, doing some demos and things like that. But at the end, I'll just kind of like wrap up and show you a little bit more about how to do that. get it working. So the first thing I want to do is talk about gRPC concepts and what gRPC is. So gRPC is a framework for creating RPC, or remote procedure call servers, that you can use to create services within an architecture. Most often this is kind of used in a microservices kind of architecture, or a service-oriented kind of architecture. And what RPCs are is they're basically like a function call, so like a regular function call, but it actually happens over the network and goes to some service and then comes back with the response, and you can use that in your application. So you can imagine many different types of services calling remote procedure calls on different other services and talking to each other in a pretty complicated manner. And gRPC runs over HTTP2. So HTTP2 is the newest version of the HTTP protocol. And that provides a number of benefits that gRPC can take advantage of. I'll talk a little bit more about HTTP2 in a second. So most of you have used REST before, I think, probably, or heard of it in terms of creating HTTP APIs or web APIs. But at Google, we use internally we use RPC a lot, and the reason why we do that is because we think that creating an RPC service, or using an RPC service, is quite allows you to has a number of benefits, and one of those is that it allows you to create very well-defined services that can be allow you to do things like generate code for clients and as well as the server side, and so it saves you a lot of time and makes development much easier. So I'm going to talk about HTTP2 a little bit, and kind of talk about why gRPC uses it and what benefits it gives you. So HTTP2 is used by gRPC to communicate between the client and the server side in your remote procedure call in the framework. HTTP2 was basically a text-based protocol, but HTTP2 is a binary protocol, so it's not very easy to see it over Telnet, but it provides you a lot of benefit in terms of actually compressing things and making things smaller and making the requests happen faster. So it's binary and it's encrypted by default. So usually what you do is you have it, you connect over HTTPS or on the HTTPS port, and then you upgrade to version 2 of the API that way. HTTP2 is multiplexed. So what that means is that on a single connection, you can do multiple requests at the same time. So normally what you would have to do before with HTTP2 is you would have to do a request, and then you just have to wait for the response to come. And then once the response comes, you can then do another request afterwards if you have the HTTP keep alive working. But with HTTP2, you can actually do several requests, and then process responses and make new requests in a asynchronous way, so that you don't have to actually wait for responses to happen. So that allows you to use a lot less connections. What you used to have to do with the browser or with any other type of HTTP client is create a bunch of connections that you can use in order to do operations in parallel or to make requests in parallel. But with HTTP2, you can actually reuse the same connections over and over again. And this has a lot less overhead and just gives you better performance. HTTP2 also allows you to compress headers. Things like cookies would be sent on every single request for HTTP, whereas HTTP2 you can actually you don't have to send the same requests or the same headers over and over again. You can send them only when they change, And also you can compress those so that it compresses those so that they're actually smaller. So you can actually have a smaller, each request is actually a smaller number of bytes. Also, like gRPC doesn't really use it, but like Speedy, the protocol that informed or most influenced the creation of HTTP2, HTTP2 can also push resources to the client. So like before in HTTP, you would make a request for an HTTP page, and then you would get the page, and then you would read it, and you figure out which JavaScript and CSS files you need to get to load the page, and then make new requests for it. But HTTP2 and Speedy would allow you to send the HTTP page and then say, by the way, you're also going to need these pages or these files also, these JavaScript and CSS files also, so I'll just send those all to you right away, instead of actually having to make multiple requests after that. So that's kind of nice. That works mostly for browsers and things like that, but it's something that's handy. The next thing I want to talk about is protocol buffers. So protocol buffers are actually the protocol that, or the main format for the data that gRPC sends to the server. So protocol buffers are a way of serializing data to send over the internet or over the wire. So you can think of it much like you would use it much like you would JSON data for REST services, but you can think of it more of a much more structured format, so that it's easier to parse, easier and faster to parse. It's very similar to formats like message pack, if you're familiar with that, but it's a very flexible format, so it supports like adding new fields without breaking backwards compatibility. And it supports things like add-ons for like code generation and for different various languages. So this is what a protocol buffer's definition looks like. So here I'm defining a message, which is a person. This is a very simple example, but you can see here it has 3 fields. It has a a name, a ID, and a email. So and 2 of these are strings and 1 is an integer. So you kind of define these much like you would in a regular program. And this will actually define the how your person is going to be serialized into some binary, into the protocol buffer's binary format. So here if you have 1, 2, and 3, these are the field numbers that are used when serializing to the format. So protocol buffers also allow you to specify things like, create things like services. And services are a set of functions that you are going to define to, that your gRPC server supports, or your RPC server supports. So here I'm defining a getMe function, which just basically returns a person, and that person is me, right? But it returns the person object that we just defined in the previous slide to the program. And so you can imagine that like you would have some sort of function like this, and that a person, you would have some sort of person class maybe in Python that has 3 fields like name, ID, and email, and that when you call the getMe function, you'll get back a class object, or an object that has those fields on it. Okay, so how do we actually create the services in Python? So Python has a gRPC, there's a gRPC implementation for Python. And so in order to use that, what you need to do is like, you need to actually download the gRPC repository. So gRPC is an open source library or open source framework. And so it's there on GitHub. And so anybody can take a look at the source code. And so to get started, you would download or you would clone that repository. And then you can actually just build the code there. We're working on making it a little bit easier to install these, but this is basically the way that you need to build it right now in order to build all the proper plugins that are used for gRPC. And so once you've had that created, and installed, as well as installing the protocol buffers compiler. Protocol buffers you can use the protocol buffer compiler to compile the messages and the services objects along with the Python plugin to output some Python code. And so here, the proto-C compiler is taking in some protocol buffers files, the ones that we created, the person and like say the person and the service files, and then generating some Python code that is used for the client and the server part of the application. So this would actually generate some, in this case it's actually a Hello World application, but it would generate a Hello World Python file that you can import like any other type of package. So I'm actually going to just jump out and show you what that looks like a little bit. So bring this back and let's see here. I'm going to mirror my screens again. And the Wi-Fi is being a little bit funky. Okay, let's fiddle with the Wi-Fi. Interesting. That's interesting. All right.
Check your Wi-Fi. If it's doing test, then you can connect to SSH.
Yeah. In which one?
What kind of Wi-Fi do you connect?
I'm connected to the Nuri guest. Oh, it doesn't support SSH. You're kidding me. Well, okay. All right. So I'm going to go in here and see if this helps. And let's see. See if I can make this bigger. No, not really. Can you read this? Maybe. So what I'm going to do is I'm going to look at this Hello World here. And so this, in here, what we have is we have like a, actually this is just some Python code. So let me look at the, Git local git. So this is actually rotos. So here is a protocol buffers file. So just taking a look at this, you can see that we have a couple of things like in the top. These are some extension type of directives for generating Java code and things like that. But so we'll kind of ignore those. But here we've defined a service which is called greeter. And so this is basically a hello world application. So we're basically just going to do a hello world. And this guy will greet us. So you can actually do a say hello command by sending it a hello request, and you get back a hello reply. So the hello request and the hello reply are basically both like our person message. So we can see that the hello request just has a simple name string, and the hello reply has a simple string message. And so this is pretty simple. So we can use this protocol buffer to actually generate some Python code. So I'm going to go back to my directory. So here I'm going to actually run the protocol buffers compiler to on that protocol buffers file, and then generate some Python code. So here I'm giving it the Python plugin that's used to generate the Python code. And once I do that, I'll get out this hello world .pb2 file. So this is the generated code from the protocol buffers. And so if you look at that, it's pretty ugly, but it's generated code. But in here you can see things like request, like hello request, and so this is actually like creating a hello request class that we can use, and a hello reply class. And then there's some other server and client related classes that are created. So if we actually go over to our greeter server and check out, this is the code that you would write. So actually, where's the import? So here, you would import this hello world pb2. So you're importing the file that was generated by protocol buffers. And then here I'm creating a greeter. This is my service or my server that I'm going to create, and I'm extending the greeter servicer, which is a class that was generated for me, and I'm defining the say hello method. So here's my actual implementation of say hello. So here I'm just saying hello. And then saying hello to whatever name was sent in the request. So if I sent hello Ian, I sent Ian as the name in the request, it would say hello Ian and send that as the response back to me. So it's a really simple a request and response kind of thing. But you can imagine that this could do some even more complicated things, like go out to a database and get some data, or get some person data, or something like that. And then down here at the bottom, I'm actually just defining a method that I'm going to use to start my service, or start my server. So here I have a server service, and I give it the port number that I want to run it on, and I just call start. And here it's just kind of waiting so that to keep the service running at all time, or continue to run it like a daemonized process. And so that's good, but I can also, protocol buffers will also generate, and gRPC will also generate client-side code. So how do we actually connect to the client-side code of that? So we can see here that I'm doing the same thing as on the server. I'm importing the PB2 file, which was generated by protocol buffers. And here I have a run method that I'm just calling when I run this particular Python file. And here I'm going to create a greeter stub, which is basically just a client object, and then use that stub to call this and call the say hello method on the client stub. So this is the method that was generated for me, and this will go and connect to the server that I've defined here, or with the IP address and port that I've defined here, and actually make the request to the greeter service good one. Yeah. So so to the service, and then print out the response that I get back. So pretty simple. So here, if I decide that I'm going to, let's actually just see if I can start up another SSH here to start up the server and see if we can get this actually to work. So in my greeter client, I had an IP address here, stub. So here I'm going to delete this and then just put in localhost. And here, hello world. I'm just going to run the greeter server here. Okay, so the server is started. And then, so my greeter client is now set to connect to localhost. So when I run the greeter client, that should connect to the server, and then here you can see that it printed out the response. So this is pretty simple. Like, I'm just running the greeter service locally on my my machine, and I'm able to connect to it and get a response back. So here, if I do the greeter client again, and then I say name equals, let's say PyCon Korea in this case, then I can run this again and get back hello PyCon Korea. So we can see that it's actually connecting to the service and actually working. So that's good. But let me go back to actually do the presentation again. So now we have a service that we can actually run, and that's with a server and a client that we can actually run. But how would we actually deploy this? We want to make something that can be managed and scaled easily and won't be too much of a burden to us when we actually deploy this into production. So that's why. So I want to talk a little bit about containers and Kubernetes and the concepts behind them. Some of the problems that it solves. But first, I want to talk about basically the way that people usually develop applications now, like without Kubernetes or without containers, and then kind of compare and contrast them later. But this is a particular kind of typical web service that you might see. Or the architecture diagram for a typical service. So here you see a set of web servers. Maybe you have a cache and databases and separate batch servers. So you've kind of created a bunch of servers here to make sure that each one of those services don't interfere with each other and cause performance problems and things like that. You don't really want your web server to get slow when you're doing batch processing and that sort of thing. So the way that a lot of people do that is, or have done that in the past, is by running things on shared machines. Or if they don't separate it, they would run things on shared machines. So you might run several apps on one machine, but you don't really get any isolation. Like I mentioned, you could have like problems where if you ran your batch and web server at the same time, when you're running your batch process or your batch service or program, it might cause your web server to become slow during that time. So you don't really want that to happen. But you don't get that kind of isolation when you're using shared machines. You also don't get like kind of namespacing and breaking things up. And also all of your labs, your applications are using the same set of common libraries. So if your applications depend on specific versions of libraries and things like that, you can kind of get into trouble. App A needs version 1 of the library, but app B requires version 2 of the library, and then you're kind of stuck. So your apps are pretty highly coupled to the operating system, but so what a lot of people do is then they start using virtual machines. And virtual machines allow you to isolate the different applications so they don't cause problems in terms of resources for each other. So like your batch process running in a VM, in one VM isn't going to take up too much memory or CPU compared to another VM, or for your web server running in another VM. But this is expensive and it's inefficient. It's running a full container or a full kernel inside of your VM, which means that you're actually you're running a full operating system. So it's hard to start and stop the app. It takes about 30 seconds to start a VM, so it's very hard to scale that up. And so and you're still like pretty highly coupled to the guest OS, like what's actually on the kernel or what kernels you're actually using. So that's kind of hard to manage, and so that's one of the reasons why Google and a number of other companies have developed the kind of technology that underlies containers. And containers have become really popularized recently by the Docker project and other projects that have started to make it easy to package up and run containers. But the fundamental technology has been around for quite a long time. And we at Google kind of see containers and container clusters as kind of a way of balancing in between VMs, or infrastructure as a service, and platform as a service. So we think that VMs and infrastructure as a service give you lots of flexibility. If you run VMs, then you can run anything you want in the VMs, and you can install any type of software you want. But you need to make sure that you manage those servers. It's harder to manage those servers, and to scale them up and down, you have to manage the servers themselves as well as the processes that are running on the servers. And so it becomes like it's pretty hard to manage, and so it's not very agile. Whereas platform as a service is very agile. It's very easy to use and to deploy, and you don't have to manage the servers themselves or the software installed on them. You just have to deploy your application and have it run. But there's less flexibility. You can't just install any application you want and just run it on your platform as a service. You have to kind of make your app fit into the platform as a services model. So if you've used things like App Engine or Heroku, like those type of platform as a services really make you choose the way that you can, you have to make your application architecture fit into that model. But containers are kind of give you a little bit of a balance point between the two. So you can run any type of software that you want within a container and within a container cluster, but you don't. But you can also get a lot of benefits in terms of how you actually deploy that container. So you don't have to actually manage where the container runs and things like that quite as much. And you can use a lot of lot of tools and APIs to actually deploy your app and scale it up. So we've reached like kind of an ideal situation where we have here an app, and each app is kind of segmented off and given isolation in terms of resources so they don't affect the other applications, as well as each app can have its own libraries and things like that that don't affect the other applications. But they run on a shared kernel, which means that each one of these runs and like starts and stops basically like any other process. So you can start and stop these things very quickly. So that allows you to start up new web services or start up new services and scale out very easily, as well as run like things like batches and things like that very quickly. And we like this type of idea so much that pretty much everything at Google runs in containers or uses container technology. So everything from like Gmail to web search to maps, all of our batch processes, all of our storage and databases all run within containers. We even run our compute engine VMs as KVM processes in containers. We pretty much run everything within the Google infrastructure in containers. And we launch basically 2 billion containers a week within our huge infrastructure. And the reason we do that is for a lot of reasons, for like performance, repeatability. It makes it very easy for us to manage the processes that are running in our clusters and schedule them and things like that. We think that this is like kind of a fundamentally different way of managing applications. So last, I want to talk about Kubernetes. Kubernetes is a open source project that is to build a container management service or a container management application that currently it uses Docker containers and supports multiple different types of cloud environments, so AWS and Azure as well as Google Cloud. And it's written in Go, so it's very fast and low overhead. So essentially what Kubernetes does is manage and schedule the servers or the containers inside of a set of VMs or servers. So if you have a bunch of servers in your cluster, you can then tell Kubernetes to run your container in the cluster and then have Kubernetes schedule that container in the cluster and run it. So Kubernetes, like I mentioned, is an open source project. We're working with a lot of other service providers, like most notably CoreOS and Red Hat. But we're also working with other companies like Microsoft and IBM and HP to build Kubernetes. And we recently reached 1.0, so we think that people can use use Kubernetes in production. So I want to talk a little bit about some of the concepts with Kubernetes, and I'm going to jump through these so I can kind of show you what Kubernetes is like at the end as a demo. But what Kubernetes does is basically it will schedule and manage what's called a pod. And a pod is a set of containers that are run on the same physical host, so the same node. So if you have multiple servers in your cluster, these containers would be run on the same machine. So they're very close to each other. So you would basically put in 2 containers inside of a pod that needed to communicate very quickly together or work together easily. So one of the patterns that we see we use this kind of idea a lot at Google, and one of the patterns that we see is that you have a web server and a kind of a sidecar container, something that does maybe SSL termination or does something like update, periodically do a get pull to update your application. Kubernetes also has replication controllers. So replication controllers are a way of managing the pods. So you can basically create a replication controller and tell it the information about your pods that you want to create, and then and how many pods you want to create, and then it will create that number of pods in the cluster and make sure that they are always running. So if one of them crashes, it will restart it and that sort of thing. You can also attach labels to each of the pods. So this way you can manage what type of application is running in each of your pods. When you create a replication controller, you can set the label that you want to have your pods use, and then later you can actually use that label to define a service. So a service is a way of defining a type of a service or a microservice. So a service gets an IP and a port, and then you can connect to that service. And then it essentially will connect to one of the pods in that match the labels that you give it, and so that will allow you to do things like load balancing and to scale out a particular application, but have a single endpoint that allows you to that clients can use to connect to it. So I'm going to go back here and demo what that looks like a little bit. So let's see, where did I have that? Actually, it's on my local machine. So here I have a definite. So when you're using Kubernetes, you create each of those objects in Kubernetes using a definition file. So you can create a front end replication controller using YAML or JSON. Either one is okay. And so here I'm creating a replication controller and I'm giving it a name and a set of labels that I'm going to use. And then down here, I'm going to tell it which information about the pods that I'm going to create. So here, I'm giving the name to my containers, as well as telling it which image I'm going to use when I deploy it. So this is actually my my Hello World application that I've created as a Docker image. And then I'm going to expose a port that so that for my service. So when I actually go ahead and create that, which I have no cluster for that, crap. This is going to take forever. All right. So while that's actually creating, which is going to take a few minutes, we'll take a look at the service. So once I've created the replication controller, that's going to create a bunch of pods in my cluster, and then that service is going, and then I can define a service that connects to those pods. So here I'm going to create a replication controller for my gRPC service, which will start up a number of instances of my service or of the gRPC server, and then I'll create a service that creates an IP address and a port that can then be used to kind of load balance over that service, so that then I can scale it up and scale it down without too much of an issue. And here I am also specifying that this service is a type of load balancer. So this will, when I use it in services like Google Cloud or on AWS, I can actually create load balancers for this service automatically, so that I can connect to it from outside of the cluster, so that regular users can actually connect to it. So this is actually going to take a while. Ta-da. So on Google Cloud, what you can create you can use a container engine, which is our managed version of Kubernetes. And what that does is allows you to create a cluster, which will create a number of VMs for in your cluster. Here I just created one that's only one server, but you can give that any number like 10 or 20 or 100, and then what it will do is it will install all of the necessary components for Kubernetes on it, and then allow you to connect to it via an API. So what that does is basically allows you to install or to use Kubernetes without actually having to install it and get it running yourself, because it can be kind of tricky to get the networking and things like that working. So here, okay, so now that my container is created, or my cluster is created, and you can see I have like a VM instance running here with Kubernetes installed on it. So now I can use the kube control command to get the pods that are running in it, and you can see that when I've just created the app that there's no pods running in it. So here I'm going to create the front end replication controller. And once I've done that, the replication controller is set to create 2 replicas. And so that's actually creating 2 pods here. And so those are actually going to get started running. So what it's doing now is it's actually downloading the Docker image to run it. But once that's running, I should be able to connect to it via using the client generated code that I had. This is taking a few minutes. So let me get set up actually. Let me also go ahead and create the service. So here I can see that my service is created, and this will also create a load balancer that I'm going to use to connect to the service, and that'll come up in a second also. That's odd. Present on machine. Container pod. That's taking a long time to get up running. So here's the service IP that I'm going to use to connect to my service. So going back here, I'm going to go to my Hello World guy here and go to the greeter client, and then put in the IP address of my service here. Let's see if those pods are up and running. That's kind of odd that they're taking a long time. Created with Docker ID. Where can you started with Docker ID? Huh. Okay, so here my pods are actually running now. So I should be able to use this greeter client to connect to it. So if I run this, it actually is able to now connect to my service running in Kubernetes and actually make a request to it via the load balancer. So you can also do things like really cool things like let's see, what's the thing here? Skill replicas. So you can do things like what is it? Fridge. You can scale the replication controller up so that you can add new replicas to it in order to scale up your application. By resource, by argument, or file name. So one of the things that you can do here is like actually change the number of replicas in the controller. I'm like blanking on how to actually run that right now, but you can imagine just running adding more pods to your replication controller and to scale up the application. So that makes it really easy to do things like scaling up your application. You can also add more VMs to your cluster in order to scale up as well. So that's basically a really easy way to manage and deploy your app. So going back. So that's pretty much all I had. So if you, I think I might have like a minute or so for questions, but I've kind of taken a lot of time. But I'm going to be doing an open space after this. So if you, to talk about, the contents of the presentation, like GRPC, Kubernetes, as well as like Google Cloud and stuff like that, here on the 4th floor. I don't remember exactly what room it is. Okay, he'll tell you what room that is. And then, so if you have any questions, I can maybe take them now. But if you don't get your questions in, you can come and talk to me at the open space. Thanks a lot.